Hello friends, welcome back to Scientific Blunders, where you learn the don'ts first. So let's say there's a company, okay, and this is a very small company, so there are only three people in the company, A, B, and C. And let's say A is the boss, and B and C are the people who report to the boss, okay? And let's say this very small company is building a particular product. It could be anything. Let's just say it's some random product that they're building. And B and C work on the product in parallel, which means so A is the boss. A is not going to do any work. B and C are going to do the work for the boss, and they're going to work on it in parallel. And the product can only be finished when both B and C are done with their work. So let's say B takes 6 months, for example, and C takes 8 months. So the product can only be finished in 8 months because both B and C have to be done with their work. So essentially, in more mathematical terms, it's the maximum of the time taken by B and the time taken by C. Okay, and so obviously we know in the real world nothing is deterministic in nature, and what I mean by that is there's always uncertainty. So A, as a boss, should always be concerned about time because time is money in business. So A goes and asks B, how long are you going to take to finish your part of the project? So B says, okay, so it's uncertain, but I could take anywhere up to a year, but I think on average I'll be done in half a year. So half a year is 6 months, right? So let me just scroll down a little bit here. Okay. So let's say X. Let's say, so we are going to use probability notation here. So let's say X is the random variable that denotes how long B is going to take to finish their part of the project. And so he says, or he or she says, the expected value of X, right, is half a year, because they're unsure. They could take up to a year, so anywhere between 0 years to 1 year, but on average they think they'll finish it in half a year. And so the boss says, okay, fine, that's fine. And the boss goes and asks C the same question, and C says, okay, again I could take up to a year, but I think on average I'll be done in half a year, right? So again, let's say Y is the random variable that denotes how long C is going to take to finish their part of the project. So the expected value of Y is also half a year, right? And now the boss is thinking inside his head. So he says, let's say the new random variable is the max of X and Y, right? Because for me to launch the product, I basically need to have both B and C finish their work. So it's basically the maximum of X and Y. X and Y are both uncertain, but on average they're 0.5. So the boss says, okay, so it's the maximum of two things, right? On average, X is going to be 0.5, and on average, Y is also going to be 0.5. So, so the boss would say the expected value of Z, or the expected value of Z is the maximum of 0.5 and 0.5, right? Because on average X is 0.5 and on average Y is 0.5. So the maximum of 0.5 and 0.5 is also 0.5. And so the boss is basically come up with a conclusion that on average their product is going to launch in 6 months, right? So I want you all to pause for a moment, and I think whatever the boss did is perfectly reasonable. It's a very, very natural thing to think. But I want you all to pause for a second and think whether this is actually correct. And so hope you're done pausing and now you're back after having thought about this. So what obviously the boss is really busy, doesn't have time to do actual math when you're running a company. But since we have time, I think we should definitely approach this problem a little more mathematically, right? So what we can do, let's scroll down a little bit, is, so let's think about it from the point of view of probability distributions, right? So let's say X was how long the first person was going to take, right? To finish their part of the project. So let's say X is the duration that they take, and f of X is the probability density, right? And so I think it's very reasonable to model this as a uniform distribution between 0 and 1. So they could take anywhere, and where X is in years, right? That's what we mean. So X could take any value from 0 to 1, and on average X will be 0.5. So what person B over here, what person B said is perfectly correct, because I think it's fair to model this as a uniform distribution. And so the average of this is going to be, by symmetry, it's going to be the midpoint. So the expected value of X is 0.5. I think there's nothing wrong with that. Okay. And if you think about it, Y is basically, Y is, obviously it's a different person who is going to do that work. But in all aspects, they are going to be identical, right? So Y is again years, and this is the probability density of Y, and that's also going to be from 0 to 1. So person B is also going to take some amount of time between 0 to 1 years, and on average they're going to finish it in 0.5 years. 0.5. And so the expected value of Y is also 0.5, and that is perfectly reasonable, right? Because we are modeling this as a uniform distribution. So I think, going back to our original problem, I'm certain that this is correct and this is correct. Now what I'm not sure is, when you're let's try to actually compute the distribution of the random variable Z before we conclude what its expectation is going to be. Okay, so yes, let me scroll down right here. Okay, so now let's think about what the distribution of Z or Z is going to look like. So quick diagram here. So Z is again years, alright, and it's the maximum of X and Y, right? So let's just think about a few combinations. X could be 0.3, Y could be 0.7, X could be 0, Y could be 0, X could be 1, Y could be 1, in which case the max is 1. And the other extreme case is when X is 0 and Y is 0, when the max is 0. So if you consider all possible combinations of X and Y and took their max, you will realize that the max of X and Y still lies between 0 and 1, right? And what we want to do is to compute the average, not using intuition like we did here, but let's just try to do it more mathematically to check whether this number is correct. So to do that, a very common technique is to compute the distribution function. So what is known as the CDF, or the cumulative distribution function. So this might sound a little complicated, but let me try to break it down for you. What we're basically doing is, let's try to compute the probability that the random variable Z is less than a particular value, small z. Okay, and how do we do that? Let me clean this up a little bit. So how do we do that? So for the random variable Z to be lesser than small z, Z is the max of X and Y, right? So for Z to be less than Z, we can say that this is equal to the probability that X is less than Z and the probability that Y is less than Z. And because X and Y are independent, we can just multiply them, right? So because Z is the max of X and Y, for capital Z, the random variable, to be less than small z, a particular value, both X and Y have to be less than that, because Z is the maximum of X and Y, right? So now this is basically to calculate the probability of a continuous random variable. It's just the area under the curve, right? Yes. And so the area under the curve is just, this is 1. Oh, not sure why I forgot to label that, but this is 1. The area under the curve is just the area under the rectangle for a particular value of Z. Let's say that's here. So it's the area of this rectangle. And so that would be what? That would be 1, excuse me, this is 1 and this is z, right? So this would be z, and the probability that y is less than z is identical, right? So you consider some arbitrary z, and then you want this area. So that will be again 1 times z. So z times z is z squared. Awesome. So this is the probability that z is less than z, right? And this might be a little bit of a review, but once you have computed the cumulative distribution function, all you have to do to find the actual distribution of z is to take the derivative of this. And I'm not sure if we have time to do like a more rigorous treatment of this, but this is a fairly standard result that once you have computed the cumulative distribution function, to get the actual distribution, all you need to do is take the derivative of this 2z, and this is fairly standard. I would really encourage you to try to understand this, and this is, I'm sure, available in almost all of the standard textbooks. So g of z is 2z. Isn't that interesting? Because if we were to plot that, that would look something like this, right? Where it's 0 when z is 0, and it's 2 when z is 1. And so if g of z has this distribution, right? So let me scroll down, and this is where we are going to find a very interesting result. The expectation of z by definition is by definition z times g of z dz, and z goes from 0 to 1. So g of z is 2z, so 2z squared dz is 2 times z cubed by 3, going from 0 to 1. So it's 2/3. So this is the average, and that makes sense, right? Because the distribution is skewed to the right. So the expected value of z is not 0.5, but it's actually, what did we get here? It's actually 2/3. So that means, on average, B is going to finish in half a year. On average, C is going to finish in half a year. But on average, the product can only be launched in 2/3 of a year. And 2/3 is how much? It's 0.67. So it's 2/3 of a year is actually 2/3 times 12, which is 8 months, right? So what is going on here? B on average finishes in 6 months. C on average finishes in 6 months. But for both of them to finish, or basically the expected value of the max of x and y is 8 months. So why is this happening? And I would encourage you to think for a second, pause the video and think for a second, because this is very, very interesting and a very important result, I think. So what is going on here is that if you think about, whoops, I think my screen froze. Okay, that's all right. So if you think about what's happening, x can take any value from 0 to 1, y can take any value from 0 to 1. But when you're considering the max of x and y, let's say x took the value 0.8, okay? Or let's say y took the value 0.8. Then for any value of x less than 0.8, the max is still going to be 0.8. So 0.1 and 0.8, the max is 0.8. 0.2 and 0.8, the max is 0.8. 0.3 and 0.8, the max is still 0.8. So there are just so many more combinations where the max will be to the right, or the max will not be in between, but it will be to the right. And that's why on average the max is not in the middle at 0.5 years, but it's towards the right, a little more to the right, at 0.67 years. And so I think the biggest takeaway, I was really amazed when I first learned about this, and I think the biggest takeaway from all of this is that max of x and y is not linear. So if z, what was that? Okay, so if this was months, right? If z is linear, then expected value of z would be expected value of x plus expected value of y. But if it's not linear, that's not true.